Okay, everyone, it's my pleasure today to have Albert here. He's coming from the E department, and he's going to talk for nice decentralized optimization tools, which personally I'm very excited about. So I look forward to hearing more details. So one big thing that I would like to say in terms of background, you have done a postdoc in Lehigh in Northwestern, where you also took your postdoc and excuse me, your PhD, and before that you was in Cornell. So just because of time constraints, by 4:30 we need to finish. I will let you start. Thank you so much. It's a pleasure to have you.
Thank you so much. Thank you for the introduction. Thank you for the invitation. Confirm you're speaking language, English. Okay.
Are you sure?
I will try my best to keep it all in English. So, as Basilio said, what I'm going to do today is talk a bit about the work that we've been doing the last, I would say, 6 or 7 years in decentralized optimization. This is joint work with many people over the years, and so I'll tell you a bit of a story as we go along. Right now. So when I give presentations, I'd like to have my first slide be this, talking about the team. I don't do research by myself. I do research with a team, and so this is the phenomenal team. I thought that at least my 2 PhD students would be in person, but it's raining, so nobody will. The rest of the team is Chengli Zhang. She's a master's student in the department, and then I'm working with 2 undergraduate students. In fact, at the moment now I'm working with 7 undergraduate students, so we've expanded quite a bit. And of course, as you all know, the University of Michigan is highly interdisciplinary, and so here I have a list of other collaborators, and they're all across the North Campus. So what do we do as a group? We design, analyze, and implement algorithms for continuous optimization. I'm a nonlinear optimizer by training, so what I see when I think about optimization is a following objective function. Minimize some function f of x. You can think about f being nonlinear and a constraint set c. Now, why do I care about this problem? Well, because it arises in a lot of cool applications and methodological areas like derivative-free optimization, which was a lot of my focus in my PhD. Machine learning, we all know that optimization is a pillar of the success stories of machine learning. And then distributed optimization, and this really should not say distributed optimization, it should say decentralized optimization, but this is a non-slide. One thing that excites me about all these problem areas and nonlinear optimization in general is that there's challenges that are important. They're hard to deal with, but there's commonality. So when we think about machine learning and derivative-free optimization, one commonality is that we cannot compute the true gradient at every iteration. And so there's transfer knowledge between these areas. And that is another reason why I've chosen to work on these 3. And of course, today what we'll do is we'll focus on the last one, from its decentralized optimization. Okay. So again, I'm a nonlinear optimizer by training. So if I were to put on these Venn type diagrams, all the research projects that I've done, the big circle is nonlinear optimization. And then you see other subfields. So these distributed, derivative-free, and machine learning right there. And of course, this overlaps. And so that's past and current research. I can show the same picture with current and future research. And I only do this to show you the breadth of the research that we're doing in our group. But the other thing that I wanted to mention is that we're going to focus on this topic today. Right. By the way, feel free to stop me with any questions at any point. And so here's my disclaimer for the day. You don't need to read everything that's written below. I was just trying to be funny, and usually I'm not. But the disclaimer is the following, that I went through the list of all the seminars that you've had in the control seminar, and I said, oops, I don't fit in. Everything was more applied. You were solving real problems, and I'm just going to show theory and algorithms. And I'm not even going to mention the word control many times, and so that's my disclaimer of the day. Okay, but I will try and bridge decentralized optimization with control as much as possible. And again, please feel free to stop me if you have questions. So our journey in decentralized optimization started many years ago when I was a PhD student at Northwestern. Raghu Bollapragada, who's actually on Zoom, and Nitish Keskar, we were in the same lab, and we took our main Professor Wei's class on decentralized optimization, and that was the beginning of the end. And beginning of the end, I mean, we started working on this field more and more and more. And so we published 2 papers with our main. And then what happened, we said, well, okay, we all moved to other places. So I moved to Michigan and Raghu moved to UT Austin. And we said, well, okay, we moved, but this research topic is super interesting, so let's continue working on it. And so we have a big team that's working on these projects. So there's a team at the University of Michigan and then a team at UT Austin, and we're collaborating very close. Today, what I'm going to do is I'm going to talk about a project that's the work with Raghu and his PhD student Shagun. And I should mention at this point, even though Shagun is not on the Zoom, that Shagun did most of the work. So if you have any difficult questions, email Shagun. Don't ask me. No, I'm joking. And what we have is 2 preprints that are under review at the moment. And I'll talk a lot more about these ones. And so here's the outline of my talk today. I'm going to do motivation and overview. Then I'll talk about decentralized gradient descent. And actually, let me ask a question. Anyone heard of decentralized gradient descent? Okay, perfect. Then we'll talk about decentralized gradient tracking methods. So 1 level up, more sophisticated algorithms. And then I'll end with some final remarks and extensions. And what I'll try and do throughout the talk is show you that our algorithms are advanced, adaptive, and flexible. That was in my title. I promised that, so I'll try and do that. I'll try and deliver. Okay. Yeah. Perfect. So motivation. Here's a problem setting. We are trying to minimize an objective function f of x that's decomposed as sum of functions. Right. And now you look at this problem and you might ask me, there's nothing distributed about that. It's just a finite sum optimization problem. True. But with that, let's now think about a network structure. So now what we have is nodes 1 through 7, each node has a piece of that objective function, and we're trying to solve the problem all in one piece. Okay. So we have our objective function is d-dimensional, so it goes from Rd to R, and then each of these component functions that we have, known only to each agent I, is also a function that goes from Rd to R. Okay. Why do I care about decentralized optimization? Well, applications, right? I say this, and people in my department probably laugh at me because they say, well, you're one of the least applied people in the whole department. But we are really motivated by applications. There is a ton of problems where we need decentralized optimization techniques to tackle them. And I'll show you 2 examples.
Is information exchange?
Absolutely. Yeah, great question. So we're going to be able to exchange information only along these edges. And so usually what we do in decentralized optimization, or one thing that we can do in decentralized optimization, is recast the same problem that we had as a consensus optimization problem. And so what we do is we decouple the problem now. Notice that in the past, what we had is fi of x, and now I have fi of xi. So everyone has a local copy of the objective function. And in order to make sure that the 2 problems are equivalent, we need to add what is known as a consensus constraint. Right? And under the assumption that our network is connected, like the network that I have here, then the 2 problems are equivalent. Okay, are we happy with that? And so just to make the notation easier, we're going to use this type of notation. So it's an equivalence between xi equals xj for all I and j that are neighbors to write an equation of this form or a constraint of this form. And it's a linear constraint. Right? And just to ease the notation a bit, so this W is a matrix that defines the connectivity. So the entries Wij are greater than 0 only if there's a link between the 2 edges, I and j, and 0 otherwise. And then this is the natural Kronecker product that's needed just to make sure that the equation is the correct dimensions. But what we're going to do is we're going to hide all that dependence and we're just going to call it Z. And so think about a consensus matrix Z that's trying to make sure that your local copy X, and so X is a concatenation of all the local copies, is equal to the average in some sense, at least at optimal. Now, these algorithms have 2 parts to them. There's a part where you do local computations. And so what node I would perform local computations on their local objective function, fi. And then the other thing we need to do is that we need to couple these problems in some way. And so what we do is there's neighborhood communication. So if there's an edge between 2 nodes, you can communicate information. Right?
And those are binary.
Those are binary.
1 or 0, not.
Oh, no, they're weighted. They're weighted. And I'll make that more explicit in a moment. You can think about these W's as trying to do an average. So in a fully connected network, you can think about having weights of 1/n in that whole matrix. And that's the best possible case, but of course it's not efficient in terms of communication. Great questions. So anything I miss in my slides, I get a question, which is perfect. So when we think about decentralized optimization, and this is where I have the word control in my slides, so I get a check mark for that. Originally, the original works that happened in decentralized optimization actually didn't come from the optimization community. They came from the controls community. So initial advancements. There was groups at MIT, there's groups at Arizona State, there's groups at Stanford and Berkeley that did a lot of the work. And so when we think about traditional decentralized optimization, people were looking at problems of the following form. Maybe not drones 50 years ago, but same kind of applications, coordination of multi-robot systems. And in that setting, what we have is that computations are cheap, and they're cheap because you can't afford to do anything more on a chip that's on a drone, for example, that's flying around. Actually, maybe now you can, but in the past. But what's the bottleneck here? What's the issue is that the communication is expensive. It can be noisy, it can even be adversarial. Okay, so we have a problem. The problem on the left is a problem where you have cheap communications, but expensive, cheap computations, but expensive communications. Figure on the right doesn't look very much like machine learning. I just wanted to show you an architecture of a multi-GPU system. When we look at this system now, communication is really cheap. Why is it cheap? Because you have a whole host of GPUs connected by high bandwidth cables, right? But what's expensive in the machine learning world is that each of these GPUs might have, I don't know, 10 billion data points. And that's not unreasonable with modern day applications. Right, so what's the bottleneck here is the fact that we need to do computations on these huge data sets. So this is my slide to show the IOE department that I actually do work on applications somewhat. The reason why I put this slide here is not to do that, is to motivate that there's other differences as well. So what I've shown is that there's differences in terms of communication costs and computation costs, but there's other differences. Here's one. With Professor Alcontar in IOE, what we like to do is build cakes. We want to optimize cake manufacturing. And so what we have is we have our design space. We don't know this objective function beforehand. We don't know the objective function that captures taste versus ingredients. And so it's a black box function that we're trying to maximize in this case. And what we're going to do is we're going to use 3 chefs and tell them, you pick one design, another chef picks a different design, and third design, work independently, and then communicate information, exchange information to learn the best design. So in this setting, really, all of these FIs that you had in the objective function were exactly the same, but we didn't know them. So that's the challenge there. So another dimension of decentralized optimization. And finally, with Professor Bayman in mechanical engineering, we were trying to build predictive models using machine learning of the hybrid buses on our campus. Here's the problem. We had so much data that it didn't fit in Renav, the PhD student's laptop. And so we needed to think about how we put data on different machines and how they talk to each other. Okay. So I've shown you that decentralized optimization isn't just one thing. It could be very different in different applications. And building good algorithms, in my opinion, and our collaborators' opinion, requires you to understand the problem setting and what you're asking for really well. And so I'll try and do that for the rest of it. So here's a literature review of a bunch of algorithms. So I mentioned DGD earlier, so it's up here. The only reason I put this list isn't for you guys to read it, just to mention that really this talk is going to focus on the second one, right? We're going to focus on linearly converging methods, and I'll talk more about what I mean by that. The other reason I do this slide is because I want to put this disclaimer. So there's been a ton of work on federated learning. How many of you have heard of federated learning? Everyone, right? It's a cool thing to do. When I was a PhD student, I wanted to do federated learning as well. I wanted to be cool, part of the cool kids. I didn't do it, but the reason why I have a disclaimer here is that federated learning is in fact a special case of decentralized optimization. And so we need to be careful when people say, well, there's all these advancements in federated learning. Federated learning is a very special case. And what is that special case? It's a special case of having a fully connected network where everyone can talk to everyone, or where you can pass around data. So in this talk, what we'll do is we'll talk about decentralized optimization, general network structure. We're going to think about different communication and computation costs. And again, as I mentioned in my title, I'm going to try and do advanced, adaptive, and flexible. And the way we're going to do that is by looking at gradient tracking methods, so these linearly converging methods, and have algorithms that are endowed with flexibility in terms of communication and computation. So remember I said that the cost could be different? Well, if you have an application where communication is 1,000 times more expensive than computation, maybe you don't want to do a one-to-one match. And then finally, we provide sufficient conditions. This is Shagun's work and also show the benefits empirically. So, decentralized gradient descent. It's been studied for many, many years. I think this is a seminal paper by Titiklis and Berahas, but there's other papers as you see here. And so decentralized gradient descent basically is gradient descent for the decentralized setting. And so what it does is, as you see here at the end, you're going to take a negative gradient step. So that's like doing gradient descent in the centralized setting. But what's different is this first part, and this is where mixing happens. And so what we have here is for every node at every iteration, we're going to take a step along the negative gradient direction. So that's what I call my computation. And my communication is what's happening with this first term. Right. And so Wij is greater than 0 if j is a neighbor of I. And I should have said here that it's between 0 and 1. And Wij is equal to 0 otherwise. So if there's no edge between I and j, then Wij is equal to 0. Now, for the most part, you can think about it. Right now, you can think about Wij being the matrix that defines a fully connected network. So you can think about, for the moment, Wij being 1 over n. Okay, so you're just doing a pure average. Now, if we use this concatenated and compact notation that I like using, then DGD can be written in the following form. All I've done is concatenated all the x's, concatenated all the gradients, and used the Kronecker product just to make sure that my dimensions work. So, what can we say about this algorithm? Well, it's a one-step algorithm. That's nice. You compute the gradient at xk and you communicate xk. That's great. Simple. You can do these two steps in parallel. So I could be sending my xk to everyone in the room and computing my gradient at the same time. So that's great. And in the case when we have strongly convex functions, so the nicest possible class of functions that I'll consider today, with a diminishing step size, you get sublinear convergence to a neighbor, to the solution. And I look at that result and say, okay, that's a okay result, but I don't like sublinear convergence. I really don't like sublinear convergence. And so then the question is, can we get away with non-diminishing step sizes? Can we do a constant step size? The problem there is that you're not converging to the solution. You're converging to a neighbor, right? And this is slightly different than what happens with gradient descent in the centralized setting, right? If we had gradient descent, and I can ask students from my 511 class, if you had a step like this without the z, and you were doing gradient descent, then you guys can both show, both of my students from my class, actually former students as well from my class, can show that if alpha is small enough, you converge to the solution. So here's my question back. Why can't we do that here? Another student from my class. So why can't we do it? Why can't we prove exact convergence with a fixed step size on that on that step? The reason is the following. When we do gradient descent, you're at the point xk, you're computing the gradient at the point xk, and you're moving from that point xk. Now what we're doing is we're playing with the algorithm as well. We're saying compute the gradient at xk, but now have your anchor point be somewhere else. So it's like doing the gradient method with errors. So how can we fix this issue, right? Or can we fix this issue? Well, if the answer to this question were no, then it would make for a very boring presentation, right? So the answer is yes, but it doesn't come for free. And so one approach that we came up with, and this was the paper that we wrote when I was still at Northwestern, was to say, okay, we like the fact that it was one step. Let's just decompose it into two steps. Let's take the average first, or the consensus step first, and then do a gradient step off of that point yk. Now we got rid of this problem. At least we have consistency in where we're taking the gradient step from and our anchor point, right? So what can we prove in this case? Well, it's a two-step method. We communicate the gradient and we compute the gradient and we communicate, that should say yk, sorry, there's a typo on my slide. And we communicate xk. And in the case of strongly convex functions with a constant step size, we get linear convergence to a neighborhood. So I didn't do anything. I made the method harder. I made it such that now you cannot do things in parallel, and I still can't get the result I want. So sorry for wasting your time. Yes.
We should understand the distinction between one step and two steps. Both just involve a matrix vector product and a gradient calculation. So at the level of like floating point operations, this is no more expensive than the other one.
Absolutely, but you have to do it sequentially because I cannot compute the gradient here before I've done the communication. So that's the main challenge here. Yeah. But I didn't do anything, right? I still get convergence to neighborhood. In fact, in order to get convergence to the exact solution, what I need to do is now say, I'm not going to be communicating once with my neighbors. Well, at the kth iteration, I'm going to communicate k times. So I'm going to send information k times at the kth iteration. So if you run 1,000 iteration, you need to communicate 1,000 times. That's not great, right? And why did we need this communication to increase? The way to think about why this algorithm doesn't work, whereas gradient descent in the centralized setting works, is because what happens is everyone has their own objective, right? Think about every xi being xi star, right? So we're not moving. Then we do an average step. We bring all the nodes closer. Now we compute gradient steps. We're moving away again. So that's the issue that's happening. And by doing this, increasing communications allows us to make sure that iterates are not moving too far. But we weren't satisfied by this. And this is by no means, I couldn't come into the seminar today and say, well, look, by the way, this is an advanced algorithm. You guys would left and probably leave. And so what are we going to do? I'm going to show a different class of methods. The only thing I wanted to put on this slide is to show you that if we think about DGD, it's that red line that's right up there. And this is a simple test quadratic problem. If you actually end up doing this one communication at every step and increase the number of computations every k, so that's the green line I want you to focus on, then you get linear convergence to the solution. So I didn't lie to you, or our theory seems to be correct, right? Now, when we think about cost, now the game changes, right? I was just looking at iterations, but really what we care about is cost. And so for every different application, what we need to understand is what is the cost of communicating and what's the cost of computing. Right. But again, this is not an advanced algorithm. I don't like the fact that when I consider cost, my green line is up here. Right. So we need an advanced algorithm. So let's talk about advanced algorithms. And I'm going to focus on gradient tracking methods. I'm not saying that those are the only advanced algorithms in decentralized optimization. Those are just ones that we like. And so same kind of slide as I had before, but a lot more names. It's not just DGD anymore. It's push, pull, digging, extra, sonata, next. Anyone familiar with these methods? Okay. I'm not familiar with these methods either. It's hard to keep track of a million different algorithms, but they have similar structure and similar form. And so what these methods try to do, they're again two-step methods. In the way that we've written them. And so what they do is the first step, they try to take a gradient type step. So think about yk or y0 being the gradient at the initial point. And then what they try to do is track the gradient, but not track my gradient, track our gradient. And the way to do that is to say, well, my new gradient that I'm going to use at the next step is going to be the gradient computed at that point xk plus 1. That makes sense. And then what I'm going to do is I'm going to mix with my neighbors and I'm going to take a correction factor from the previous grade. Right. Seems like a natural idea to do here. There's always questions about should there be a factor of beta there to control, because we want to think about this as a control variant. There's many questions and many adaptations, but this is just the basic. Right. Now, it doesn't come for free. Again, we need to have x and y in this case, two of these vectors. But when we think about the types of steps, we compute one gradient and we communicate two quantities, xk and yk, so double the communication. We have this additional variable yk that tracks the gradient, so we have, as I mentioned, additional communication. But the other thing is, and what we were hoping for, we finally got it, strongly convex functions, constant step size, linear convergence of the solution. So now I'm happy, or now I can sleep at night. Oh. But really, none of these methods were ours, right? So we have a reference to our paper up here, but we tried to unify all these methods. That's what our contribution was. And the reason why we try to unify all these methods is because you see, there's 3 of these methods. These are 3 of the most popular gradient tracking methods. If you are sitting really far in the back and you squint your eyes, they look the same. But if you come to the front row, I promise they're not the same. Here's what's the bigger problem. The bigger problem is that the analysis for digging and sonata and DGM is very, very different. And so it's very hard to compare algorithms theoretically. It's also hard to compare them empirically because one paper defines your optimal alpha, another paper doesn't define the optimal alpha. And so what our goal was, or our first goal of this, so the choice, what's important, the another thing that's important here is that the choice of information shared dictates both convergence and practice. And what I mean by practice is, if you look at this last equation, or last method down here, before, I cannot do these two steps in parallel. I cannot do them in parallel, right? So I need to do one and then the other. Or sorry, what I meant is I cannot communicate, like be communicating things at the same time because they are dependent on quantities that I don't have. So I need to get xk plus 1 before I can do my communication of this second step. The other thing is that the cost of communication computation steps is application dependent, and there's nothing here that can help us balance between. And so what we did, our first goal of this work was to say, we want algorithms of that form, and we want to analyze that beast. And now you'll say, well, why did you need 4 consensus matrices? Could you do it in a different way? We just wanted to have it be as general as possible. And what's nice is when you think about this general form, what you can recover is digging and extra, sonata next, and OGDGM and ATC digging, right? So all these algorithms are special cases, but of course, there's a lot of other algorithms that are not even analyzed in the literature. So we have this unified framework, and now what I want to show you is a bit more details about the analysis and how we can compare algorithms. And then I'll promise with every theoretical result that I show, I'll show some numerics as well. Yes.
This accelerate with
Gradient, a special case.
That's a really good question. It actually is not exactly a special case of these things, but I see why you're thinking about this because of the dependence on the history. Right. So it's not exactly the same, but there are accelerated DGD type methods as well. Great question. So in order to do analysis, I'm just going to define some notation. So we have our X bar, it's the average of our local vectors. And then what we'll do just to fit the analysis, we'll do a concatenation of all the same vector X bar. We're going to do the same thing for Y. What drives convergence is, of course, properties of the objective function, but also properties of this matrix of mixing, right? So if we have a fully connected network with 1 over n, we do one communication and we all have the same value, whereas if we have a sparsely connected network, that's not the case. And so what we care about is the second largest eigenvalue of these matrices, which is dictated by beta. By the way, the largest eigenvalue of these matrices is 1. And then everything else is magnitude between less than 1. And so we care about the second largest eigenvalue that's between 0. Our error metric, or what we're hoping to prove convergence on, is a vector of this form. And why do we care about that? Well, because the first term there tells us that the average is going to the optimal solution. And the second and third one's telling us that each local copy that we have is going to the average. And so we put these two together, it's exactly what we would like. Okay. And I'm going to make assumptions, the nicest possible class of functions. You can extend these results to other settings, but it just gets more complicated. And so we're going to assume that each function is mu strongly convex and it has Lipschitz gradients. In fact, I'm going to assume that each fi has Lipschitz continuous gradients just to simplify the result. Okay. So the first result is the result that I alluded to earlier. It was the fact that if you have a sufficiently small step size, then this error recursion is going down at a linear rate. I'm not writing anything new other than the last bullet that I had on the DGD slide, or in the digging slide. What's interesting and what we cared about, though, was to compare these algorithms head to head. And so if you run all the algorithms with the same small step size, then you can prove the following results. So these are upper bounds for the rates of convergence for the 3 algorithms, or 3 classes of algorithms. And so these rates have a maximum of 2 terms. And if you notice, the first term looks very, very familiar to the convergence rate of gradient descent, off by a factor of 2, but that's not important. And so that is really your speed limit. You're never going to be able to go faster than centralized gradient descent. And then you have a second term that depends on all of the things that you don't want a result to depend on. For example, the condition number. Condition number can be scary, but at least you have this factor of beta in there as well. So beta, remember, was that factor, the second largest eigenvalue is between 0 and 1. And what's important here is if you look at these three second terms in the maximum, the placement of beta is very, very different. Beta up top doesn't affect the condition number. Beta on the bottom affects the condition number, but not the Lipschitz constant. And then beta at the bottom affects everything. And so when we first derived these results, I was saying, okay, where's the typo? It cannot be this clean. It doesn't work out this clean, but it does work out this clean. And when you look at this, you say, okay, so if I could pick any of these algorithms and implementation wasn't an issue, what would I do? GTA 3. And so the network structure beta affects the convergence, and you can show that the rate of convergence is faster for GTA 3 than GTA 2 than GTA 1. I'm not lying, or at least this experiment verifies, and I do believe that the proofs are great. And so what we have here is optimization error and consensus error. So think about the first term in that R vector and the second term in that R vector. And what we see is that GTA 3, which is the blue, is performing better in terms of iterations than both green and red, which are GTA 2 and GTA 1. And this is on a network that's almost fully connected. By the way, if we had a fully connected network with 1 over n everywhere, then the beta value there is 0. That's a very, very nice case. Now, when we change the beta, and we change the beta to cyclic network, so think about just a circle network where you have 2 neighbors, every node has 2 neighbors, then what we see is that the behavior starts to change. It seems like GTA 2 and GTA 3 perform almost the same, exactly the same. In fact, in GTA 1 is worse. And again, the reason for that is the placement of that. When we think of consensus error, the red line seems to be, or GTA 1 seems to be performing the best. But of course, if we were to run it longer, I think the green and blue would overtake. Right. So that is an algorithm, but I still haven't talked about advanced. And sorry. So this is where I wanted to say that this is what I mean by advanced. Okay, so I 3 promises. I kept my first one about advanced.
So Albert, if your network is a cycle, what's the beta for that?
If the network is a cycle, the beta is 0.922 here. For a network with 16 nodes. So think about this. This would be, in this setting, you would have your W matrix be a tridiagonal matrix.
What if your network is just a straight line?
So it's even worse. You get a worse.
It's a little worse, but it's not 1.
It's not 1, it approaches 1. Yeah. Great question. Great question. So I think if you have a connected network and all the entries are between 0 and 1, then you cannot have that to be equal to. You have 1 eigenvalue and 1, everything else is 1. Okay. So I did advanced, now I need to do flexible and adaptive. And so what I was trying to motivate at the beginning of the talk was the fact that we have different decentralized optimization problems, and different problems have different costs for the 2 operations. And so what we're going to do is try and incorporate multiple communications first, and then we'll try and do multiple communications and gradients in just a moment. And let me just show you what is happening. Oh, by the way, Marie, here's your example. So we have a W, and I've constructed it in this way. And if I were to do 2 communications, so everyone exchanges information twice, effectively it would be result in a network that looks like that. And I can show the exact W matrix for 2 communications by taking this matrix and squaring it. And so this was tridiagonal. Now we have extra diagonals there. Okay. If I were to do 200 communications, and this goes back to why near DGD, or that algorithm that does increasing communications, work. If you do 200 communications, what happens is you get this matrix, and that's a pretty nice matrix, right? Fully connected, you're just average. So what we wanted to do, and this is where we talk about flexibility and flexible, what we're going to do is we're going to do exactly the same step that we had, but instead of communicating once at every step, we're going to communicate NC times. We're going to see what's going to happen. Now, the Z matrix changes, the W matrix changes, which means the Z matrix changes, and that effectively changes the beta value that we have. And remember, that beta value is between 0 and 1, so beta to NC is greater or equal to 1, is getting smaller and smaller, so we like that. So with more communications, i.e. an increase in NC, the step size will increase and the rate of convergence improves. And in fact, remember this result that I showed earlier? It's exactly the same result. I just changed it up because I'm going to add something to there. So we see the betas are sitting right there. Ideally, what we would want is now all these betas to be raised to the power NC. Is that wishful thinking? No, that's exactly what happens. And so again, this makes me really happy. Okay. So the number of communication steps NC affects the convergence rates, and when we plug in NC is equal to 1, we recover as a special case what I showed there. Okay, both in terms of this result, but also in terms of the step size. Okay. So one point of flexibility is there, and just to show you a couple of experiments, what we have here is the same problem as before. Now, instead of just doing the benchmark lines that were the circle with the circle markers, now we have the triangle markers, and 5-1 means that you're communicating 5 times in computer units. Okay. And so what we see here is in terms of optimization error, the methods don't, the performance doesn't change too much. With GTA1, it seems to have an effect. It has a negative effect in terms of the optimization error. That's not too surprising. But in terms of consensus error, you're communicating more often, so all the methods are better. Right? So that's not surprising. Now, of course, when I tell me, Albert, you're cheating. You're comparing a method that communicates 5 times with a method that communicates once, and you're putting iterations. It's as if the costs are the same. It's not the same to do the 2 methods. And so we need to be thinking about putting communications on the x-axis as well. And so when you do that, now what you see is that in terms of optimization error, the triangles are worse, right? But again, what's important and what I'm trying to say here is that if you have an application, you might know the costs of the 2 operations. And so you can dictate what you want to do. Again, when we look at consensus now, we see that these triangles are better. And of course, it makes sense. We're communicating 5 times. Okay.
I missed that point. What's the intuition behind optimization error increasing?
The intuition is that you're getting pulled closer to the consensus and not closer to where you want to go. Remember, our optimization error was something like x bar minus x star. And so you're getting moved away from the average.
May I ask?
Here, you're also doing more work, right? Because here we're measuring it in terms of, so this, even if the 2 algorithms were exactly the same in terms of iterations, when we consider communications, one should be 5 times worse, right? Because the x-axis.
Yeah, a good question. It goes a few slides back where you say, okay, I have the line network, but effectively, if I communicate many times, this becomes like a click. What's the assumption? Is this this is because the underlying assumption here is that we can relay messages, right? So essentially, the 4th will hear about the 1 after 3 rounds, right?
Right. So you cannot directly communicate, but you can exchange information. So 4 to 2 through 3, essentially. But on a high level, and once we don't know that 2 and 4 can't communicate, you could think about it as just a different W. So instead of starting with that W, I could have started with this.
Well, thank you so much.
So, if the weights on these edges are very different from each other, I mean, I can kind of, if you don't show me the actual numbers and you just show me 2 pictures side by side, I was like, yeah, I'm totally buying into it. But if the weights are actually different, then like, to what extent does the intuition still go through, right? Because if I'm sending a message twice over a couple of weak channels as opposed to 1 strong channel, like it's not all the same.
Yeah, absolutely. You're absolutely right. I mean, this isn't a street case, right? Where I put so much weight on the diagonal, which means you care about yourself more than your neighbors. I could have done this and put a third everywhere. And that would mean that when I do multiple communications in that setting, I would get to the fully connected 1 over n setting much faster. So with lower number of extra communications. But because of our assumptions that our matrices are nice and they're doubly stochastic, so row and column sums are equal to 1, you can guarantee that eventually, so no matter where you start off from, when you do enough communications, you'll have fully connected. Does that answer your question?
Well, it's fully connected, meaning that it's dense, right? So like
Should be
there's
1
no
over n.
zeros. Okay, but how long, like what power you have to raise everything to get to that effect does depend on actual weights.
Absolutely.
Okay. Okay.
Absolutely. Great questions. Show this, I showed this. So really, again, back to flexibility twice I showed, so. So what we're gonna do here is we're gonna do the same exact thing, multiple communications. We like that, it worked out well, but now I want multiple gradients as well. Why do I want multiple gradients as well? Because the cool kids in federated learning are doing. Right? And so what we do is you do a bunch of steps where you're just communicating and taking steps, but then what we do is ng number of just gradient steps without communicating at all. So there's no Z matrices down. Now, what does this do other than just create a huge headache for Shagun because the analysis is much harder? Well, it gives you flexibility, right? It gives you flexibility. And really the complications arise because the way that these decentralized algorithms work is, okay, take a gradient step and then consensus. Take a gradient step and consensus. So you're not allowed to move too far away. Now we're saying NG gradient steps. NG gradient steps, I could have moved from here to central campus with NG steps, right? So that becomes a problem. The other thing is, as I mentioned, it's an important setting in practice.
We can add more complication if you want, and in general, depending on how much computation power and communication power and heterogeneity in the network you have, you might have multiple NCs and communicate more in one channel and less in the other channel. Do more iterations in one compute node and less iterations in one compute node. So flexibility.
So that I would love to be able to do. My last slide is talking about asynchronous variance, and that was my really adaptive algorithms. But yeah, that's exactly what I would like to do. I would like to have enough information about the application itself so I can quantify the costs of the two and also each node. For example, if you have a node that's connected to every other node, that node should be communicating probably. If you have a node that's only connected to one centralized node, maybe that person should be sending gradient information, should be computing and sending gradient information. So it really depends on the application, but that's exactly what I want to be able to do.
You might have a wired connection between two nodes and wireless on the other.
Absolutely.
They can just communicate a lot here.
Absolutely. There's a lot of settings. That's why I like decentralized optimization, because you can have three of you have the same objective function, or the three of you have completely different objective functions. The two of you are connected with a network, you have the same, and then someone else has an adversarial objective. So there's a lot of settings, and it's application specific, I think.
Or to take it in another direction, one of your nodes could be running off battery power and another one could be running from the main line. And so they should save their energy and not communicate as often.
So I love this discussion because this is exactly why we got into this field. We wanted to say, okay, let's create algorithms that are flexible as possible, and then people can customize them to their specific applications. And so what we can show in theory here, and again, don't even try reading what it says there. All it's saying is that if you have an NC that's greater than 1 and an NG that's between 1 and infinity, then there exists an alpha, small n alpha that you get linear convergence. Well, basically, it's a generalization of the result that we had before. And again, you can derive corollaries about step sizes and convergence rates. Everyone would have hated me if I put the full results here because they're super complicated. What's important, again, is GTA 3 is better than GTA 2 is better than GTA. And that we can also see in the experiment. So again, we have the baseline methods 1-1, then we have the methods that do 5 communications and 20 computations of every iteration. And what we see is that in terms of iterations, I really like that line. But I'm cheating when I put that blue line. I'm doing 20 times more computations and 5 times more communications than when I was looking at GTA 3 with the circle. And so we need to think about what this means when we look at gradient evaluations. We need to see what that means when we're looking at communications, number of communications. And in fact, what I think we should be looking at is a combined cost. If you know your cost of communication, if you know your cost of computation, the x-axis here should be really a combination.
So that even a crude model where you say as a function of the communication and computation cost, this is what I estimate my overall energy or time or something cost to be.
Yeah, so what we did is in a couple of applications, especially that first paper that we wrote where we needed to grow the communications to infinity asymptotically.
Yeah.
We got a comment saying, well, we don't want to be doing that, of course, we agree. And so what we did is we took a toy example, a logistic regression problem, and we calculated the cost of computing a gradient. And so that was time on my machine. And then we artificially put delays in communicating. And so we showed for different values of the communication delays or how long it takes to communicate the performance of the different methods. So really what we had on the x-axis was cost. So another thing that we did, and I put adaptive now, so it's the third thing that I promised, was to say, well, we want to do these two steps, but we really like to be like the cool federated learning kids, and we want to do these probabilities. So with the probability P, we're going to do communications. With the probability 1 minus P, we're just going to compute. And this is exactly what they do in federated learning. And so what ends up happening here is that the method is less rigid and achieves a balance only in expectation now. So the results are not deterministic, it becomes a bit harder. We have good theory and empirical performance, so we still get linear convergence in expectation now. And again, what it does is that this framework also recovers popular gradient tracking. And so one experiment here that I wanted to show is for a fully connected network, because I wanted to mention again, this disclaimer that I said at the beginning was that the cool kids of federated learning is a special case of decentralized optimization with beta is equal to 0. Right? I really like beta is equal to 0. It makes my life easier because you could treat all these algorithms as centralized. And so FedAv, SCAF-new, scaffold, these are all popular methods in machine learning or federated learning. And so I'm showing the performance on, again, the same quadratic in terms of gradients and communications. And of course, some of these methods are really powerful in terms of communications, but in terms of computations, they're not that powerful. And so we need to be careful. The other thing is if I don't have a fully connected network and I want to apply these methods, the only one that we can apply is SCAF-new. And after days and days of tuning, Shagun, the best result that Shagun could get was, okay, you're doing okay on optimization error, but look what's happening in terms of consensus error, a low parentheses. Why? Because this method was not built really for this setting. Okay. So what I'll do is I'll take a couple of minutes to wrap up. We have a decentralized optimization of this form, and I presented a unified gradient tracking framework that was adaptive, advanced, and flexible. Promised 3 things, and I delivered 3 things. Well, flexibility so far. The framework was endowed with flexibility in communication and computation steps, and we were able to show fast convergence rates. I don't like sublinear rates of convergence. I'm allergic to sublinear rates of convergence. They're way too slow. And the reason why is because I don't know how to set the step size. 1/k, not a great thing. The other thing was that these methods were efficient and robust in practice and across a wide range of applications. I only showed quadratics for 16 nodes with small dimensions, but in the paper we have a lot more experiments. We did logistic regression and other problems as well. Now, one thing I wanted to mention is that we've been working on this for maybe 7 years now or 6 years, and every time we write a paper, and I think Raghu, who's on the call, will agree with me, every time we write a paper, there's another 10 questions that arise. I like that about research. That's a good thing, I think. The other thing that happens is every time that we write a paper, there are new thoughts and ideas from applied domains reaching out to us saying, well, can we have adaptivity in terms of who communicates and who doesn't communicate and so on and so forth. So a lot of the times at this point, we respond to saying, well, this is the baseline analysis that we have. We would like to build something better and stronger. We would like to have asynchrony as well. Right now it's a heuristic. Right? But with that, again, there are a ton of open, interesting questions. Students that have taken my 511 class will probably see this presentation and feel a bit bad because I talk about how constant step sizes are a bad idea and that we should do adaptive step sizes. I talk about how first order methods are myopic and I don't like them and let's do a second order method instead. And many other stochastic functions is another one. And so here, I only showed first order methods with constant step sizes. And so really, I do want to extend these methods to other settings. I want to do adaptive step sizes with a line search. I want to do stochastic functions. I want to do second order information in the methods. I want to do constraint problems. Now that becomes really challenging. I want to do asynchrony, and I'll show one slide on asynchrony. I want to do adversarial networks. What if people are trying to compete with each other? Right? I might send bad information to my neighbors. And then quantization. And quantization is interesting because you might think about quantization when you're far away from the solution. I don't need to share my true information, but as I'm approaching the solution, maybe I do. So 3 more slides on extensions, and this is where I talk about really adaptive problems. So we started off with this network, right? And here's the question that I want us to ask. Does one really need to communicate across all edges at every iteration? Right. Here you might say, yeah, there's not too many edges, but think about a fully dense network. Do you want to communicate across all the edges? Is it necessary to do that? And the answer is no. So instead of doing a step where you're mixing with the Z matrix that we had, think about Z tilde being the Z matrix where some points, some elements that were non-zero in that Z matrix, I'm zeroing them out. And let's do communication in this way. And so what we have here, and this is slightly written in a different way. So think about average spectral gap is 1 minus beta that we had, right? So originally we wanted smaller to be better. Now larger is better. And what we have here is a pruning threshold. And so this is 10% of the non-zeros we make zero, 20% and so on and so forth, all the way to 90%. And so what ends up happening here is I've pruned, let's say, 40% of the edges that I had. So 40% of the non-zeros are now zero, but the beta didn't change too much. So if that's not, if the beta is not changing, and we know that the beta has a huge effect, then why would I be communicating with everyone? So that's one thing. The other thing is that this is not just we played with linear algebra and I showed you a matrix where this happens, right? You actually see these gains in practice. So ACGT, think about it as the adaptive algorithm that I talked about earlier. But now what we're doing is at every iteration, I'm either pruning 90% or 50% of the edges. And so what we see here across the board in terms of optimality and consensus error in terms of gradient evaluations and communication, what we see is that this blue line seems to be performing really, really well, right? In fact, it's performing better than the line with 0.5, right? And 0.5 is the one where we're pruning much less. So what this is telling us is that while you're given a network, someone gave you a network that you can use, you don't need to be using every single arc at every single iteration. Okay. One more thing, and this goes to the question. What I really want to do, and this is again really adaptive, is we have different agents or different nodes in the network. And I want each of these nodes to be deciding what they're doing independently of what's happening to everyone else. So node 1 has decided a gradient step, then communication. And what you see is that on the x-axis here, I have time, right? So what you see is that these gradient computations could be fast or slow. And there's multiple reasons why that could be the case, even within a node, right? But the other thing is that what we see here is that nobody's waiting, no node is waiting for any other node. And that's important. Think about having a distributed system where the algorithm that I showed earlier, where we have to wait for everyone. And so you have one bad node in that network. Suppose that I'm really bad at computing gradients. You guys all have to wait for me. Right? So that becomes a problem. Now, this is wishful thinking. This is what we started off with. And we have now some preliminary results. And I know it's very small. All I want you to take away from this slide is that blue is an algorithm where every node is deciding what to do independently of everyone else. So that's that blue line. And the algorithms that I've been presenting earlier are really the red and the orange line. So the orange line up here and the red line down there. So it does seem that there's ways to do asynchronous variants of these methods where nodes are, of course, communicating to each other, but they're not locked. And so with that, I'll end off with my favorite slide. Thank you so much. I'm happy to take any questions. You have a lot of cooking.
I think we have time for 1-2 questions because you need also to go.
Yeah, I'm happy to take a few.
I have a question for, like, what is the intuition behind we use consensus form in optimization? So why is it?
So that's a really good question. The reason why I like that consensus form is because it decouples the problem. And now every node has its own thing. Let me just show you the picture that I had. So the original picture had different nodes and each node just had the function. Now each node has the function and a copy of the iterates. And so now what I could do is I can decouple the problem completely. So you have your fi and xi, your neighbor has fi and xi, and so on and so forth. And in order to make sure that they're the same, all the xi's, that's why I put the consensus constraint.
So this is a must, I think.
This is a
Must.
No, there's other ways to do it, right? I'm sure there's other ways to do it.
And may I prioritize also a little bit on Zoom? Let's see, I think
there's
it's
one
because
question.
the people on Zoom, they don't have the same chance to ask a question.
Oh, a very long question. Read it out. All right.
I think so, I will do that.
Okay. In your exploration of adaptive consensus within decentralized networks, have you looked into the potential of leveraging game theory concepts such as mass equilibrium or cooperative games solutions to optimize communication strategies? The quick answer to that is no, but I would love to chat more. Specifically, how might these concepts inform the development of an algorithm that dictates when and how nodes should communicate? I don't know how to answer the second part of the question, but I would love to chat offline. Whoever wrote that message. Oh, perfect. I got a thumbs up.
Let's do one more question and then we can break it. And yeah, depending on your,
I have a technical question. So apparently, like the performance depends on the weight matrix. Do you have a way to design the weight matrix, like to minimize beta, for example?
Well, that's a really good question. So you're saying if I tell you the network structure, so you know what the sparsity pattern should be, can you give me the optimal weights to get the best beta? Yes, there's people that are working on that.
I see.
In our domain, we thought about it more so that some domain expert has given you a matrix, but you can actually optimize the matrix. It is a challenging optimization problem, but certainly one that you can attempt to solve. Yeah.
let's take the speaker.
Yeah, because beta is like this. But because like this like this is a specific form. I don't know.
I'll send you an email.
I'm asking. It's been more on centralized gradient using for the gradients.
Okay.
So now.